Alright, after having seen a couple examples of perfect square trinomials that are simple, as in have an a value that equals 1, we're now going to look at some perfect square trinomials that are complex trinomials. So remembering that complex trinomial means the a value does not equal 1 for a trinomial of that general form. In terms of verifying that it's a perfect square, the actual steps we're going to take will be the same. So we first need to know if the first and the last terms are perfect squares. And you'll notice I didn't put the checklist here because I want us to kind of remove the need to have that when we're actually doing these problems and start just having that in your memory. Are the first and last terms perfect squares? So let's check that. For the ax squared term, that's going to be 4x squared, but the square root of that. So square root of 4 and times the square root of x squared, that's just going to be 2 times x, or 2x. So that is a perfect square. The shortcut to you being able to recognize this is ask yourself, is the coefficient a perfect square? And does the variable have an even degree? So this is degree 2, which means yes, it's an even degree, and 4 is a perfect square. So we could have also just said that, automatically we know it's a perfect square just by inspection. And then the other, square root c, so the square root of 49 is going to be 7. So that's also a perfect square. So that's good. And we know that the first and the last terms are perfect squares. So that was one of the conditions that we had to meet to prove it's a perfect square. That was kind of like our first step. And then second piece of proof that we need is we need to know, since this is a positive middle term, we need to know if the middle term, we have to check that 28x equals 2 times the square root of c times the square root of ax squared. So I'm just doing a left side, right side check and doing that algebra, or really doing the equivalence testing to see what we get. So 2 times 7 times 2x. So this will be 14 times 2x, which will be 28x. So that's also a check mark. So we've now proven that the trinomial is a perfect square because we've proven that the first and last terms are perfect squares, and we've proven that the middle term is equal to 2 times the square root of this times the square root of this. So really, this is just one way that I think is helpful to represent it because we know that we're used to seeing trinomials in this form. This is the exact same thing. It's the same concept with just a slightly different representation. So we've actually proven we've proven this by doing this. We know that this middle term can be gotten by multiplying the a squared and the b squared. So same idea, just different representation, that's it. So now that we've verified it, we can actually factor it using those quick strategies. So 4x squared plus 28x plus 49. Now that we've done the verifying work, we can just pull out a and b values because we've actually already figured out what they are by doing the verification. So 4x squared is going to be the ax squared term, and then 49 is going to be the b squared term. So since we've already done the work and we should be comfortable by now just kind of pulling this out of the trinomial, we know that a is 2x. We found that over here, and we know that the b term is 7 because we found that over here as well. So we've proven here a squared plus 2ab plus b squared equals a plus b squared. So that means for this expression, 4x squared plus 28x plus 49, it's going to be equal to 2x, because that was our a term. So 2x plus 7 squared. and then that would be the final answer for the factored form of that trinomial. So again, you could have used, if all you're being asked to do is factor, then you can just use the strategies from previous lessons to factor this and it still works. However, if you have that mental math piece down really quickly, then this is actually the most efficient way for you to factor a trinomial if you can prove that it's a perfect square. If you are asked to verify a trinomial as a perfect square, then you do need to do this work. But if you're just given this and told factor, then you don't have to do this. This is just an additional strategy that we're reviewing because it's more efficient. So now we're going to look at the most complex example where we have a complex perfect square trinomial and there's more than one variable at the same time. However, don't let the additional value or the larger numbers worry you because the procedure is exactly the same. So once you get comfortable with that, you understand the steps, then no matter what trinomial you get, you can always do the verification and factor it. So I'm just writing this above because this still gives us a good structure to follow for the trinomial. We know that this is like our ax squared term, this is like our bx, and this is like our c. So again, the first step was we always have to verify whether or not this term and this term, the first and last terms, are they perfect squares. So let's check that. The square root of ax squared equals, in this case, square root of 25k squared, square root of 25 times the square root of k squared. And again, this is just the proof. We know that this is going to be 5k, so that is a perfect square. You can also just ask yourself as a shortcut, is the coefficient a perfect square? Yes. 5 squared is 25. And then does the variable have an even degree? Yes, it does, because 2 is an even number. So therefore, we know it's a perfect square. And then let's try the other one. Square root of c, that's going to be square root of 36m squared, or the square root of 36 times the square root of m squared, and that's just going to be 6m. So that's another perfect square. Again, this was just our proof. You could also do this by inspection. 36, is that a perfect square? Yes, it is. 6 squared equals 36. And then the variable has an even degree, even number degree, because it's 2. So we've proven that those are both perfect squares. And then second part is we want to know if the middle term is equal to, because it's being subtracted here, it's negative, we want to know if it's equal to negative 2 times this term times that term. So let's see. Is negative 60 times k times m equal to negative 2 times the square root of c times the square root of ax squared? So this will be equal to negative 2, and then the square root of c was times 6m times, what was this one, 5k. So that will be equal to, I'm just going to pull out the numbers first, make that a bit easier for us. This expression is equal to negative 2 times 6 times 5 times m times k. You don't have to write it this way. I'm just pulling all the numbers together because when you have a complex expression like this, it means you have to multiply everything by each other. Like you have to multiply all the numbers together and all the variables together. That's a common theme in our course. Look at the number part and the variable part at the same time. So negative 2 times 6 is going to be negative 12 times 5 times m times k. Negative 12 times 5 is negative 60 times m times k, which is negative 60 mk. And then again, because of multiplication properties and how the order that you multiply terms in doesn't actually matter for the answer, you can just rewrite this as negative 60 times k times m. So the left side does equal the right side, so there's our second verification. We've now proven that it's a perfect square. So that was really good for us that this is a perfect square, because now we can factor it. Because if you were applying the old strategy of find two numbers that multiply to give you a times c, but then add to give you b, you'd be looking for some really large numbers there. So in this case, this strategy is very helpful for us. So we're going to have 25k squared minus 60k times m plus 36m squared over here now. And then we've proven through this work that it does fit this pattern. So this means that this is like our a squared term, that's like our b squared term, this is like the 2ab. So therefore, it should be easy for us to pull out what the a and b values are, because we've already done that work over there. A is going to be 5k, that's this one. And then the b value is going to be 6m. So this is the only thing that you need to keep in mind, and that can be confusing, is just that a squared and b squared here, the a squared term does align with the ax squared, but the b term actually aligns with the c of the trinomial. So you just got to really keep your variables straight when you're doing these types of problems. So we have 25k squared minus 60km plus 36m squared. We've proven that it fits this pattern. So that means if you factor this, it would be equal to 5 times k minus 6m squared. And that would be the final answer.